Hello, welcome back to Mastering Statistics. Here we're going to put everything together with this hypothesis testing that we're going to do involving two variances. We'll be using the F distribution to figure out how to set these tests up, and we'll be starting off with a right-tail test. And if you've been following all of my lessons in hypothesis testing, which you really have to understand this material, so go back and review that if you haven't already, you know that there are right-tail test, left-tail test, and two-tail test. And the type of test you have is really just going to depend upon the problem. So right now, our problems are going to start off with the right-tail test. Let me show you what I'm talking about. Essentially, you have this thing called the F distribution, which is the kind of distribution that we use when we have tests involving two variances. So this is the F distribution, and as you remember from the last section, it's very skewed. It has a big hump and then it has a tail off like this. And ultimately, we're going to use the concept of rejection regions, which we've used all up until now in hypothesis testing. So there's this critical value of F. We don't call it critical value, we call it F sub alpha. And the reason we call it F sub alpha is because it's the value of F that you end up reading off of the table that gives you an area under the curve to the right, always to the right, of alpha. And alpha is our level of significance, right? Which is basically related to the level of confidence. So if you're doing a 99% confidence test or a 95% confidence test, then this value of alpha is going to be different. So the shaded area will be different, and then the F sub alpha, the critical value, is going to be different for those problems also. So if you remember back, we've done this before when we did rejection regions. So there's this critical value here, and it lines up with F sub alpha here. So everything to the right, if we calculate our test statistic and we get a value over here, we'll reject the null hypothesis. All right, so if we get a value of for our test statistic over here, we'll reject the null hypothesis. Remember, everything in hypothesis testing is always, do you reject the null hypothesis or do you fail to reject it? And if you get a value in your test statistic over here, you will fail to reject the null hypothesis. So essentially, the problem is going to give you enough information to figure out what F sub alpha is, and then your data is also going to give you enough information to figure out where your test statistic lies. If you get a test statistic anywhere over here, then you're going to have enough evidence at this level of significance to reject the null hypothesis. And if you get a test statistic from your data over here, you're going to not be able to reject it. You're going to fail to reject that null hypothesis. And then in those cases, when we get to an actual problem, we'll talk about the conclusions. Now remember, for these types of problems, the test statistic, and I've kind of mentioned this before because I had to when I introduced the F distribution, is going to be F is equal to S1 squared over S2 squared. Remember, we're sampling and we're getting a sample variance. So S1 squared is the variance from population 1 that we've sampled, and S2 squared is the variance that we calculate from the data we collect from population number 2. We just divide them. That's all you're doing. You take population number 1, population 2, and you divide them. You get a test statistic. Either it's going to fall here or it's going to fall here, and this is your hurdle. This is the hurdle that you jump over. I like to refer to it as the hurdle because essentially it's telling you what number you have to cross, what threshold is statistically significant for your data. We'll get into some problems in a second. And just to kind of write it all down, if you get a test statistic that's greater than F sub alpha for a right-tailed test, then you're going to be in this shaded region, and that's going to mean that you reject the null hypothesis. Basically, it's what I wrote up here. And then if you get a value of F that's going to be less than F sub alpha, then you're going to fail to reject. Or less than or equal. You're going to fail to reject the null hypothesis. All right? So what I'm going to do now is keep this picture in your mind. Let's go on to the next slide here, and then we're going to actually do a problem to put it all together. So here's our first real problem. We have two plants, and they produce pencils. A manager thinks that plant A is malfunctioning, and that the variance, notice the word variance, in the pencil length at plant A is greater than the variance of the pencil length in plant B. Okay, so what does he do? He thinks this is the case, so what does he do? He samples 20 pencils from each plant, 20 pencils from plant A, 20 pencils from plant B. Plant A has a sample variance. Notice we use the word sample variance because we don't look at every single pencil coming off the line. We only look at 20 of them. So we calculate a sample variance of 1.45. That's a measure of how different each pencil is in length coming off the line. A bigger number means they're not very consistent. The variance in their length is not very consistent because you have a bigger number in the pencil length, the variance in the length. Plant B has a sample variance that's much smaller, 0.47. Test the claim with 99% level of confidence. Now what we need to do first before we write anything down is make sure we understand the problem. So we'll go through it again. We produce pencils, there's plant A and plant B. Manager thinks the variance, that plant A is malfunctioning, the variance in pencil length at plant A is bigger. Now look at the data. The variance in plant A is bigger. It's 1.45, and plant B has a variance in the length of those pencils of 0.47. So just from looking at it, it looks like, hey, everything that we're saying is actually true, that plant A does have a higher variance of the pencil length than plant B. But you can't, and so it would, you know, if you just look at this data, you would look at it and say, well, I just go ahead and say plant A is malfunctioning. The pencils coming off the line are not very consistent. But the problem with just making a conclusion like that based on this information without doing a real hypothesis test is that you've only looked at 20 pencils. So it's not enough just to say, hey, it looks like it's malfunctioning. What you want to do is you want to see statistically, is this significant at a very high level of confidence? I mean, if you're going to go spend $5 million to switch out the equipment in plant A, if it's malfunctioning, then you want to know with a very high confidence that this sample set with this data is really statistically significant. Because if you only measure one, let's say not 20, let's say you measure 1 or 2 pencils coming off the line, is 1 or 2 pencils enough to figure it out? I think most people would say no, 1 or 2 pencils is not enough. You have to have enough to be sure that you're right. So the hypothesis test does all of that for us, and it tells us if it's statistically significant in the result. So what we need to do first is write everything down because they bury a lot of information in the problems and we have to write the stuff down. So we, first of all, notice that it's a 99% level of confidence. So that means that C is what we call level of confidence is 99%, which when we write that as a decimal is 0.99. Okay? But we don't use a level of confidence in hypothesis testing, so we have to calculate alpha, which is 1 minus C. So just to show you 1 minus 0.99, when you take 1 minus that, what you get is 0.01. So our level of significance was not given in this problem. Instead, we were given the level of confidence. If you're given this, then you must convert it to a level of significance. Later on, when we use the F distribution table, we're going to have to make sure that we're using the correct table for alpha equals 0.01. So that's step 1. Then we want to write down the data that we're given there. We sample 20 pencils from each plant. So from plant number 1, we'll call it N sub 1. Instead of A and B, you know, you can do A and B, that's fine. Plant A, plant B. Instead, let's just call it number 1, number 2, since that's how we've been doing it in the past. We sample how many samples? 20 pencils from plant A. What do we get? We get S1 squared, which is the variance in the pencil length of 1.45. Now, first of all, how would you calculate this number? Well, if you were really doing it, you would grab 20 pencils off the line and you would measure their length. Now, they're not going to all be exactly the same length. There's going to be some variation, which is what variance comes from, in the length. So what you would do is you'd calculate the mean length, and you would use the formula for variance, which we've covered in the past, to take all of that raw data and calculate a variance. This number is basically telling you how much from the mean, it's the square of the standard deviations, you know, which is basically a measure of how, on average, how much variation we have from the average pencil length, from the mean. And a bigger number means there's more variance. Okay? So then we're going to go off and look at the other data that we have. From plant number 2, we also sample 20 pencils. We're writing everything down, and the variance that we calculate from here is 0.47. If, instead of just telling you the variances here, if I gave you all the pencil lengths from plant A that you measured and all the pencil lengths from plant B that you measured, then you would have to go back to the definition of variance and calculate it by hand, or you could dump it in a calculator and it would calculate the variance for you. But in this problem, it's given to us. All right, now just to make sure you understand and have everything written down, this is plant A, and this is plant B. Okay, so what do we do next? We have to write down the claim. right? We have to figure out what the claim is, because in hypothesis testing, the claim is basically what you think is different from the null hypothesis. It's what you think has changed, what you think is different. It's your claim that you're trying to investigate. Every real life problem is there's going to be some accepted situation, which is that the plants are behaving fine, and then there's going to be some claim. In this case, the claim is the following. So let's go ahead and draw a little line here. The claim that we're investigating is always going to be the alternate hypothesis, because it's the claim. It's what you're claiming is being different from the norm. Basically, what we're claiming is the population variance from plant 1 is greater than the population variance from plant 2. Now make sure you understand the difference here. See here, when we measured the data, I said that the sample variance was 1.45. So you see we use S here to be the variance of the samples we collected. But when we write our hypothesis test, our alternate hypothesis, we write it in terms of the population variance. This is the variance in all pencils coming off the plant. And this is for plant 1. This is the variance in all the pencil length coming off of plant 2. That's why we use sigma here, because this is the population. This is, maybe our plant produces 5 million pencils a day. We're saying that we think that the variance in the length of all 5 million pencils, or the whole population, is bigger from plant A than plant B, which is not good. But that's the alternate hypothesis because it's the claim. So once we have the alternate hypothesis written down, then we can write down the actual null hypothesis. The null hypothesis is going to be the exact opposite of the alternate hypothesis. So if the claim is up here that this is greater than that, then the null hypothesis must be the mathematical opposite of this, which means that the variance coming off of plant 1 is less than or equal to the variance coming off plant 2, right? And then I'll go ahead and write down the alternate hypothesis down below, which is what we just wrote above. Sigma 1 squared greater than sigma 2 squared. So make sure you understand this. This is important, so I'm going to kind of circle this, because this is kind of the crux of the problem. Basically, you're claiming that the variance of the pencils coming off the plant is greater from plant 1 than plant 2, so therefore the null hypothesis has to be the exact mathematical opposite. It has to be that the plant A is producing equal to or maybe less than variance from plant 2. That's the null accepted hypothesis. Now, when you're trying to figure out left tail or right tail test, you always look at the alternate hypothesis or the claim. So this guy, this arrow to the right, means right tail, which is exactly what we figured out from all the hypothesis testing we've done in the past. You always look at the alternate hypothesis. The direction of this arrow means this is a right tail test. Okay, now the next thing we need to do is write down and try to figure out what our rejection region is. But in order to do that, we need to find f sub alpha. We know that alpha is 0.01. We need to find f sub alpha from the table. And since we've already used the table, you know that it's going to be based on this test statistic, which we'll use in a second, which is s1 squared over s2 squared. The reason I write it down is because basically what we need to know is this is going to be the degree of freedom of the numerator, and this is going to be the degree of freedom from the denominator, right? So for the degree of freedom of the numerator of this fraction is basically how many samples did we take from population 1. We took 20 samples. So the degree of freedom for that is going to be 20 minus 1, which is 19. Right? Very simple. All you do is take the number of samples minus 1. The degree of freedom from the denominator is the same exact calculation. In this case, we happen to sample 20 pencils from each plant. Your problems don't have to be like that. We could have taken 15 from one plant and 12 from another. It's okay. In this case, we sample 20 in each case, so the degree of freedom of the denominator is again 20 minus 1, which is 19. So remember, when we use the F distribution table, all we needed to know was the level of significance of our problem, the degree of freedom of the numerator here, which is 19, and the degree of freedom of the denominator here, which is also 19. So now we have enough information to construct the rejection region and finish solving the problem. So let's go ahead and scroll down here and take a look at this table. Now, this is a table for illustration purposes. This is not the table that I originally used to solve this problem, but it's good for the illustration to show you what we're doing here. The degree of freedom of the numerator was 19, which is what you read across the top, and the degree of freedom of the denominator was also 19, because it's the samples minus 1. So what you're really trying to do, and I'll just sketch it right here, you're trying to find what f sub alpha is here. So let's go ahead and draw a picture here, because ultimately we're going to write down the rejection regions here. So this is the f distribution. Somewhere over here is a magic value that we call f sub alpha, and the area to the right is alpha, right? In this case, alpha is 0.01 for this problem. So we're going to read a value of f somewhere off of this chart that's going to be the value of f here to give us an area of 0.01 to the right. All you have to do is look for 19 in the numerator, all right, the degree of freedom of the numerator, and 19 in the denominator. So you look up here, you have 10, 12, 15, and you have 20. So you don't actually have 19 for the degrees of freedom of the numerator in this table. When you look down here for the degrees of freedom of the denominator, you do see 19 here. So I wanted to show you this, on purpose, because some tables are not going to be constructed as much or as well as others. This one, you have on the previous part of this table 1, 2, 3, 4, 5, 6, 7, 8, 9 for the numerator, and then it starts skipping numbers when you get up into the higher values. So you don't have a value of 19 degrees of freedom in the numerator, but you do have 20. So you come down here at 20 and intersect with the 19 degrees of freedom for the denominator, so you're going to get 3. In this table you're getting 3.00, but this isn't quite right because the degree of freedom is not 20 for the numerator, it's 19. So you would have to go a little bit this direction, closer to 15. So really it's somewhere between 3.00 and 3.15. So you have a couple of options if you don't have the exact value in the table that you have in your textbook. You can interpolate or basically guesstimate what the value is. You know it has to be somewhere between 3.00 and 3.15, and it's going to be closer to 3.00 because 19 is closer to 20 up here. You could also mathematically calculate the exact value based on the difference here, or you could just find another table that has the exact value that would have 19 up here in the degree of freedom of the numerator, or you can go to a computer and calculate the exact value, because you can calculate the value of the f distribution for any number you want without using a table, just by plugging it into Excel or some other program on the web. In this particular case, I'm just letting you know that the value is somewhere between 3.00 and 3.15 because it's not quite exact here. Now when I solved the problem the first time, my table actually did have a value of 19 up here for the numerator and an exact value of 19 for the denominator. So whenever I solved this problem the first time, f sub alpha was given by the table to be 3.0274. So this value of alpha is 3.0274. All right, which basically is exactly what we said, because if you look here at 20 and at 19, the intersection is here. We're saying it's really close to 3.00, and that's what we got, 3.0274. So that's how you read f sub alpha off the chart. Now what we need to do is calculate the test statistic to see if we're going to reject or fail to reject the null hypothesis. The test statistic, I've been saying over and over again, is just very simply S1 squared over S2 squared. It's the ratio of the sample variances that we got from the original problem. So when we go up to the original problem, sample variance for the first population, or for the first sample, is 1.45. Sample variance for the second one is 0.47. So we're going to put those two values into this calculation. On the top, it was 1.45. It's just literally a number divided by another number, 0.47. And when you do that division, you get 3.0851. So here is the hurdle that you have for this level of significance, and here is the data that you actually calculated and got from your data, 3.0851. So what we have here, if this value of f is 3.0274, then this value from our test statistic is just to the right of it somewhere. Maybe I'm just kind of guessing, but maybe somewhere right in there. So I'll kind of draw an arrow here, and I'll say f, the actual test statistic, is 3.0851. And as I told you before, if you get any value from your test statistic over to the right here, you're going to reject the null hypothesis. If you were to have calculated a value anywhere over to the left here, then you would fail to reject. So since we are in the rejection region here, we have enough information to solve the problem. So we know that f, our test statistic we calculated, was greater then F sub alpha, and it was a right-tailed test, so that means we're in the rejection region, which means we reject the null hypothesis. We reject the null hypothesis at this level of significance. So that means that at this level of significance, there is evidence to support the manager's claim. There is evidence to support the manager's claim. So let's go back up and just do a quick summary. The basic idea is we had two plants, and they're producing a different variance in the pencil length coming off the line. Now it looked like, at first glance, 1.45 compared to this, it looked like plant A was actually malfunctioning. It wasn't producing very consistent pencil lengths. It's true. But we have a very high level of confidence that we needed to figure out if it was statistically significant. So our null hypothesis was that the plants were equal, or maybe plant 1 was producing less than. The claim was that plant 1 was producing pencils with a variance greater than plant 2. What we figured out statistically is that we can reject this null hypothesis. That means that the claim that the manager thought that plant A was producing with a higher variance than plant B, there is evidence to support it. But as I've said through all of these problems and all of the hypothesis testing, it all depends on the level of significance or the level of confidence. So what we say is we can reject this null hypothesis at this level of significance. If we change the level of significance, or if we change the samples, or if we change any of these numbers even a little bit, it might change the result. If you notice, the hurdle that we have to jump over is F alpha 3.0274 right here. And we just barely, by the skin of our teeth, scraped right over the hurdle and said, hey, it's statistically, yes, it is true statistically with 99% confidence, 3.08. That's pretty close to our hurdle. If our data were slightly different, or something else had changed in the problem so that this test statistic was over here, then we would fail to reject that null hypothesis. And then we would be discarding the manager's claim and saying that, hey, it might look like it's true, but it's not statistically significant. But in this case, we do think that we have enough evidence to reject that null hypothesis and say that the claim has merit. All of these problems will be constructed the same way. I spent a lot of time on this one just talking and explaining. As we do the next few problems, it'll be a lot faster because we won't have to explain quite so much, but they're all going to be done the same way. Calculate F sub alpha, calculate the test statistic, are you in the rejection region or not, and then the problem is done.